Okay, so to wrap up the worksheet, so again, this was what was following, right? This was taking the ground state and translating it. So that is important. We get a coherent state. Notice that what we initially had was a Gaussian in position and a Gaussian in momentum. So now we're going to go through and create something else. We are going to say create Gaussian, and we are going to create a Gaussian in the position distribution. So I'll click here. Notice I have a Gaussian here. Notice I have a Gaussian here in momentum. So this is a different way of creating the state, right? Again, we don't know the details of what's happening in the simulation, but we've created a Gaussian in momentum, a Gaussian in momentum, a Gaussian in position, and notice that again, it's a superposition state. I have a bunch of different energies here. So now let's go ahead and play it and see what happens. We see that our wave function really spreads out, right? And then it comes back up, peaks, and comes back down. Notice that our momentum distribution is doing something similar, but kind of opposite. So again, it's helpful to kind of watch what's happening with our expectation value. So when our position is passing through zero, that is in fact when our momentum is at its maximum value. And when it reaches that maximum value in momentum, it really spikes up. And when the position reaches the end, it also spikes up, and that corresponds to the momentum distribution passing through zero. So again, we see a behavior here which is very similar to what we would expect from classical, except again that idea that these are different distributions. So notice that there's kind of an overall lag in time in the behavior between these two. Again, there's kind of that when one's in the middle, the other's at maximum, but that otherwise their distribution, the behavior looks really similar. Is this a coherent state? No, it's not a coherent state because we see that the shape of our distribution is changing with time. So I think this is really interesting that by taking the ground state and dragging it to the side and displacing the ground state, we get a Gaussian, something that looks like a Gaussian in both momentum and position, and it is coherent. Here, I just created a Gaussian, and it's in fact not going to be coherent. And I can create slightly different Gaussians, and each time something really similar happens, right? So why is this? So the key here is to again look at these superpositions here, that we have all of these different phases happening, and the phase is different in our initial situation of that translated ground state versus just creating a Gaussian. So now let's stop and go on to the next one, which is to create a Gaussian in momentum. So I'm going to create a Gaussian in momentum, like there. Yeah, that'll work. And so I have now noticed this Gaussian in momentum, and it's all the same color. Now look at what's happening down here, right? These phases, if you look, it's like, wow, there's like this 90-degree difference between these phases, and if I click back up here in momentum, that's not at all what's happening in my phases. So I click down here, I see kind of this weird 90-degree thing happening in my phase. Initially, my position here is more or less at zero, right? My position looks to be at zero, but since my momentum distribution here is entirely positive, it's at zero and going to be moving. We see that I've given it a fairly high average energy. And now when we let it play, wow, something really weird has happened, right? We don't even just see that Gaussian. We kind of see something with lots of weird kind of ripples, right? This looks super different than the others. So let's stop and try to create it now just a little bit closer to the center. So we again have an initial state, but now the energy isn't quite as high. And I let it play. We again see that distribution do kind of a weird thing. It's kind of still doing that spiking. We now have less motion because I've given it less energy, but we see lots of those little ripples. So what I'm trying to communicate here is that we've now made 3 different initial states that all look pretty much like a Gaussian in position and a Gaussian in momentum, but how they evolved in time were completely different. And this time evolution is heavily influenced by the phase of those coefficients for the superposition. So all 3 looked like Gaussians in both momentum and position. All 3 were superposition states of many, many, many different states here. However, the phase relationship between those were totally different, which led to different evolution in time. So many times the calculations we're doing, phase ends up not mattering because we're working with really simple systems and simple measurements. But in this case, where you start to create more complex superpositions, in fact, then the phase matters an incredible amount. So the book makes this as a passing statement, and I think a lot of students miss this on the initial read-through. To create a coherent state, you must have specific phases between all of these different eigenvectors. And in fact, it's the complex phase that matters. So it's not just now, well, what is the relative magnitude of these different coefficients, but what's the phase as well. So I hope that that's helped. The final 2 wrap-up questions were that relationship between the quantum and classical harmonic oscillator behavior. Again, I hope that you've seen the correspondence principle in work. The idea that for superposition states, for higher energies, we see higher probability near the edges, which is what we would expect. Classically, that's where the particle spends more time. We also see that we can create wave packets, which in fact do move back and forth, and the evolution in time, the expectation value of the position and momentum distributions match what we would expect classically. So once you make a wave packet, that's something that behaves more like a particle overall, and we do see its position kind of going back and forth, and that it has the highest momentum distribution when it's in the center and 0 near the end. Now, of course, we've made those wave packets in different ways, and we see slightly different behavior, but the expectation value, in fact, works really similarly. The coherent states, again, is when the momentum and position distribution stays an identical size and shape and just shifts side to side, and it requires having very specific complex phases amongst all of our different coefficients, not just the magnitude of the coefficient. So I hope, as always, that this has taught you something about quantum mechanics.